Now, chapter 5 deals with inverse functions, more precisely, exponential and logarithmic equations. No, we went to inverse functions. Section 1 of chapter 5 deals with the inverse functions because exponentials and logarithms are inverse functions. What does inverse mean? Opposite. Now, opposite in mathematics, we first use that term. If I said that x equals 3, what's the opposite of it? Negative 3. Kind of. It'll extend on that concept. First off, we have a different notation. Remember that y is equal to f of x. That's what. Now, whenever we talk about an inverse, inverses have this notation, this -1 exponent. So whenever you see that -1 exponent, that means it's an inverse. And yes, it is an opposite of the original function. And we'll show you how to prove that too. Graphically, what this means is, let's say I had a set of points. Let's say my data set of F consisted of these 3 points. This is my set of data, has these 3 points. The inverse of it would consist of these points. So what happens on inverses? Look at the first line, look at the second line, look at each point separately. What do you notice? Switch, yeah. The x of the original becomes the y of the inverse. The y of the original becomes the x. So example 1 says, here's my data set. It's made up of points 2, 4, -1, 3, -2, 0. Let's plot those points. Five by 5. So the first point is at 2, 4. -1, 3. -2, 0. So what are the inverse points going to look like? 4, 2. Very good. And 0, negative. These I'll represent with x's. So we go to 4, 2, 3, 1, and 0, -2. Now, if you drew a diagonal line here, which is the line y equals x, the 45-degree angle line, what you'll see is that these are just mirror flips of each other. 2, 4 becomes 4, 2. 3, 1 becomes, oops, that was 3, -1. I'm sorry, it's down here. So they're all equidistant away. So basically, if you were going to draw a graph of an inverse, draw the graph of the original function and fold your paper on the diagonal. And then what you have on the other side is the inverse graph. Let's see what example 2. So how do we find this inverse graph? What do we do? Yeah. Switch x and y, which is how to find the equation of the inverse. Step 1. Switch x and y. And then solve for y. That y becomes now your inverse function. So switch x and y, solve for y, and now represent it as the inverse. So let me give you an example here. Y is equal to 3x plus 2. Find y, the inverse. So what do I do? Switch x and y. Now I solve for y. And there's my inverse. Will all functions have an inverse? Which ones won't? Well, this one has one. Let's look at example 2. Well, let's look at the next example first. Let's say y equals x squared. After this, we'll define what the formal definition is. What does this graph look like? That's, I know what you meant to say is parabola. It just came out wrong. It's a squared, so we'll have two solutions and they both point up. So to find the inverse, switch x and y. That's step 1. Step 2, solve for y. Square root both sides. I have to put a plus or minus here. So the inverse equals plus or minus square root of x. because this is positive square root of x. This is negative square root of x. Remember, we're looking for inverse functions. Is this a function? Why not? No, you had it right the first time. Exactly. It doesn't pass the vertical line test. The inverse does not pass the vertical line test, the vertical line test. So it's not a function. But we knew it wasn't going to pass by looking at the original equation. What's the opposite of the vertical line? What's opposite of vertical? Horizontal. This original one fails the horizontal line test. The horizontal line test tells us this. If a function f of x fails the horizontal line test, then it will not have an inverse. If the graph of the original function fails the horizontal line test, then it will not have an inverse. Now, I know you all memorized this charts and our discussion from last chapter. So what this means is any function with an even exponent. If an exponent is even, it does not have an inverse. Why? Because remember, if the degree is even, that means both ends point the same direction. Automatically, that fails the horizontal line test. So automatically, if the degree is even of the polynomial, then it will not have an inverse because you fail the horizontal line test. We can extend it even further. It says if it has a even exponent anywhere inside the equation, it'll fail. Let's look at this. Let's look at example 2. Find the inverse. X squared minus 5x. So our first step was switch x and y. And try to solve for y. We can't. I mean, even if we factored out a y, we cannot isolate y by itself. Does not exist. Again, what's the degree of this polynomial? 2. It's even. So we know automatically without even trying to do any work, it's not going to work. So the horizontal line test. We know the vertical line test tests if it's a function. Horizontal line test sees if there's an inverse. The only way a function can pass the horizontal line test is if a function is 1-to-1. Which means for every x value, there is one and only one y value associated with it. That's what 1-to-1 means. Here's what it means. For every x value, there is one and only one y value associated to it. So any x value I pick, that y value only belongs to that x value. That y value belongs to this x value. Does that work here? Let's say this is -2 and this is +2. They both equal 0. Are they unique? No. They don't have a 1-to-1 because for this x, it's 0. For this x, it's 0. It's not 1-to-1. That's why this will not have an inverse. This one will have an inverse because for every x value, there's one and only one y value associated to it. Which is what the horizontal line test tells us. They both cannot share the same y value. So that's what that says. Let's see what the next example is. So mathematically, how do you test something's 1-to-1 without graphing it? You have a function, f of x. Pick 2 points, a and our 2 values, b. If a does not equal b, then f of a cannot equal f of b. If, this is if a equals b, then f of a has to equal f of b. That's how you test 1-to-1-ness. If I plug in 2 different numbers, I have to get 2 different answers. If I put the same number in, I have to get the same answer. That's the only way I get the same answer. So that's what that's saying. Example 2 or example 3. Graph the function f of x equals 2x minus 3. Prove that it's 1-to-1. So what's this graph going to look like? A vertical line? Yeah, it's a lot. Yeah, you had line in there. Yes. So what's the y-intercept? And the slope? Yeah, 2/1. So up 2/1. And there's that line. Is it 1-to-1? Yeah, because it passes the vertical line, horizontal line test. It passes the horizontal line test. And again, what's the degree of this equation? If there's nothing there, it's automatically a 1. So again, it has an odd degree, so it can be 1-to-1. Since it's linear, it's going to be 1-to-1. Example 4. Graph the function described here and prove that it's not 1-to-1. This is what we've done earlier. What's the graph of this look like? Exactly, the horns. Exactly. It fails the horizontal line test. All right, for the example 5, we have 4 graphs. Which one of these 4s are 1-to-1? Which one are not 1-to-1? Is A 1-to-1? Yes, because it passes the horizontal line test. B? No, it fails. C? Yes. And D? It fails it because it horizontal line test. So it's not a function. It's not 1-to-1. All right, so that was example 5. Example 6. Determine whether the function f of x equals 2x minus 3 is 1-to-1 and find its formula. Okay, here's another way of finding if it's okay. Graphing is one thing, but that takes a lot of time. Will it have an inverse? Well, we could find an inverse. This is not 1-to-1, but we could find the inverse. The inverse we can find, even though it's not correct, it should be plus or minus. But how do we test it without graphing it? How do we test if it's truly 1-to-1? This is how. First, find the inverse. So we have our original function. we have our inverse. Without graphing them, we can tell if they're one-to-one. Remember, we're using, that's the reason we learned section 2.3, the composite functions. If a function is one-to-one, then this will always be true. If you take the composite function of both of those, it'll equal x. And you should always test both of these. F inverse, F inverse, F. So let's try this. Let's take this equation and plug it in place of x. So we're doing F inverse of F first. So it's going to be 2x minus 3, that's in place of x, plus 3 over 2. Negative 3, positive 3 cancel. 2x over 2, those 2's cancel, so equal x. Check, that one works. And 2, we're going to take this equation and plug it in place of x here. 2 times x plus 3 over 2 minus 3. The 2's cancel. So we just have x plus 3 minus 3. The 3's cancel, leaving x. So those are inverses. So that's how you test if you have inverses or not. So this was actually example 7. Now, is it any secret that it's supposed to equal x? Remember, how do you know what line is the inverse and the regular graph? What is it rotated about? This one, right? What's the equation of that line? Y equals x. Y equals x. So if you take an original function and the inverse of that function and combine them and plot the points, you'll get this diagonal line, y equals x. Okay, so let's look at example 8 now. Consider the function g of x equals x cubed plus 2. A, is it one-to-one? If so, find its inverse and then graph them. So is it 1-to-1? ¿Por qué no? Yes. But which one, 10 minutes ago, we said which ones do not have inverses for sure? Even if they have even exponents, right? Because the graph of x cubed is an increasing function. That's x cubed. So it is 1-to-1. So yes, it is. Let's find the inverse. Switch x and y first. And take the cube root. So the inverse is actually the cube root of x minus 2. So let's test our two functions. So I take this equation and plug it in place of there. So I have cube root of x minus 2 cubed plus 2. This is testing. The cube root and cube cancel out. So I have x minus 2 plus 2. It equals x. So that works. Now I reverse the process. I take this and plug it in place of x in there. X cubed plus 2 minus 2. Because this is my input. Positive 2, negative 2 cancel. Cube root and cube cancel. So it works. So it does have an inverse. Let's go ahead and graph them now. Y is x cubed plus 2. Remember, the x cubed function is like this. It's a vertical shift of 2. So it goes like this. And the x-intercept the cube root of negative 2, which is negative 1 point something something. The inverse of this function is cube root of x minus 2. The cube root of x, the graph looks like this. It has a horizontal shift of 2 to the right. And here's the diagonal line, y equals x. And those are your inverses. This is y, and this is y inverse. Because if you had taken the page and flipped it over, folded it across the diagonal line, you get the other graph. Pretty straightforward. Example 9. Let's finish up this section. Given f of x is equal to 5x plus 8. Use the composition of functions to show that f inverse so here's a function, here's the inverse. How do we prove that they're inverses? Remember that rule? If they're inverses, then their composite functions will equal x. Likewise, if we take the f inverse of f. This is the only test that you can have if you have a function, find the inverse, and then do a composite function of both of them. Let's do this one. So I take this equation, plug it in place of x. Plus 8. And this other side, I take the inside function and plug it anywhere I see an x. So 5x plus 8 minus 8 over 5. So these, the 5's cancel. So we have x minus 8 plus 8. So it equals x. This should equal x. Now in this one, the 8 and the 8 cancel, so we have 5x over 5. Yep, it matches this rule. So that's how you test to see if they're inverses of each other. And besides that, on your sheet, right there. Oh, and the last section it says, remember how f of x, x squared plus 2 was not 1-to-1? We can make it 1-to-1. We can make a function 1-to-1 by changing its domain. Because x squared looks like this. X squared goes from negative infinity to positive infinity. If we only restrict it to 0 to infinity, then it will have an inverse. If I take this equation and x is greater than equal to 0 only, then I switch x and y. X minus 2 equals y squared. Now when I take the square root, it's only of the positive x's. Now it is 1-to-1. Because I took, basically, I eliminated the horizontal line test condition. The 2 x's here, I got rid of this one, so there's only 1 x. So it passes the horizontal line test, which means now it is a function. So if you have a function and it's not 1-to-1, change the domain, and then you can make it 1-to-1. By looking at the graph, of course, it makes it easier. There, QED. That's Latin for what was to be demonstrated has been demonstrated. Quid et demonstratum. Class is over. We only did 2 sections today, not a problem.